So, hello everyone. I'm Real Kajiwara. I go by Sylph01 on the internet. And this is End-to-End Encryption Saves Lives. And you can start saving lives with Ruby too. And yes, this is the right talk. The intended title was too long for the CFP. So the slides are available through this QR code, or you can find the link in the Discord, and I tweeted the URL. And there's also a Japanese subtitled slides. And I have a lot of text, a lot of diagrams, and I'm going through very quickly. So you might want to open the slides and follow it along. So I'm going to wait like 10 more seconds. OK, let's go then. Hi, or welcome to Matsuyama. I am very happy to have you all here in Matsuyama, and in my hometown. And I do a lot of stuff. If anything catches your interest, let's talk. And also, I do a lot of stuff that is more relevant to this talk. Especially, I've been working on writing, editing, and implementing standards in W3C and the IETF. So before we start, the usual disclaimer when I talk about security stuff, cryptographic API is very easy to misuse. And operational security is also very difficult. The protocol being theoretically safe doesn't mean that it is safe from operational screw-ups. You've seen it on the news. I've done my research, but I don't consider myself a security expert or cryptography expert, which means I am not DJB. So if you're not sure, please have your system audited by a security expert before going to production. And the MLS implementation I'm talking about today is nowhere near production ready. It passes, it says most, but it passes actually all the test vectors, but it lacks validation on error cases. And I've heard like validation is important in today's another session. So I'm planning to release a full version before the next IETF, which takes place on July. So, I happen to be known as the SMTP o yamero guy, which means stop using SMTP, or more like SMTP is dead. And I have two problems with the SMTP. One is it lacks strong identity, and two, it lacks end-to-end encryption. So what is end-to-end encryption is that it means the people who run the service cannot read your messages. Like your usual messaging apps like Line, Facebook Messenger, Signal, WhatsApp, they all have their each own version of E2E. And to talk about why end-to-end encryption is important, we have to mention some international affairs, so please bear with me for a while. End-to-end encryption is more important than ever because there is more increasing tension in the international affairs, and more powerful people want to control the internet, even in democratic countries. And end-to-end encryption provides a safe method to communicate under oppression and in war zones. This is what I mean by end-to-end encryption save lives. But hey, doesn't end-to-end encryption help criminals too? Like people would ask like that. And yes, end-to-end encryption is being targeted by authorities, even in democratic countries. But even if you ban end-to-end encryption, criminals will still use them because they are criminals. And banning the end-to-end encryption disproportionately harms vulnerable people. And the Internet Society published a blog post describing how encryption saves children who are otherwise vulnerable on the internet. So, HTTPS or TLS also helps criminals, but are you going to ban HTTPS or TLS altogether? Like, we can't imagine an internet without HTTPS, TLS today, right? So, yeah, here's the end of the political part, and let's go back to talking tech because this is a RubyKaigi, right? Yeah, and messaging layer security is a more interoperable version of doing end-to-end encryption, and the MLS provides key exchange through multiple parties. And messaging layer security has two documents. One is the protocol document, which is in RFC 9420, and the architecture document, which is to become an RFC soon. And today's topic is about the implementation of the protocol. And now we can say we kind of have RFC 9420 on Ruby. And because MLS brings interoperability in secure messaging, we could say that messaging layer security is essentially SMTP o yamero. And I wanted to publish a gem of MLS, but the MLS gem already exists for a defunct website, and it exists since 2012, which means it predates the 0.0 internet draft of messaging layer security, which came out in 2018. So I named my gem Melos, which is taken after a novel that is in most Japanese middle school, high school textbooks. And as it's named after a novel that talks about speedrunning to save your friend's life, we're going to any % speedrun through the messaging layer security protocol. Please know that this will be very quick, and this will omit major cases too. So MLS depends on HPK, hybrid public key encryption. And it is a form of encrypt with public key, decrypt with private key that is used in TLS, but more formalized. And it works in the combination of a key encapsulation mechanism, KEM, which is asymmetric crypto, and key derivation function, KDF, which is almost a hash, and AEAD, authenticated encryption with associated data, which is symmetric crypto. And these are available in Ruby as the HPKE gem. And there are two security characteristics that we want out of secure messaging. One is called forward secrecy, and which means messages sent at a certain point in time are secure in the face of a later compromise of a group member, which means it's secure against harvest ciphertext now and decrypt it later if we have the capability. Another one is a post-compromise security, which means messages are secure even if a group member was compromised at some point in the past. In this case, each member updates their key so that group secrets are not always encrypted with the same private key that have been compromised in the past. Okay. These two characteristics are described in this diagram. Forward secrecy secures the message of the past, and post-compromise security secures the messages in the future of the compromise. And to achieve this, in two-person groups, it's very easy. Both parties start with the same common secret called a chain key of generation 0. Then for the future generations, when sending a message, we create a message key with an HMAC SHA-256 out of the chain key. And we get another the chain key of the next generation with an HMAC SHA-256 with a different key. And to extend that to 3+ person is very difficult, because if we were to do the same method in 3+ persons, number of the edges in an n-node complete graph is O(n)², which is very inefficient. So we're going to use your favorite data structure that turns O(n) into O log n, which is trees. And we have 3 parts in MLS, and this is a diagram taken from the RFC. And this is kind of confusing because it hides the fact that there are actually 3 parts to doing MLS. One is the key schedule. So a group has a state variable called an epoch, which is like a generation. And in each epoch, then there's an epoch secret, which is updated using the commit secret. And if we assume we can get the same commit secret for each group member, we can assume that the group secret state, the next generation epoch secret, would be same among all members. So there is nothing much difficult in this part, because it's just a lot of chaining together a lot of hashes. The second part is the secret tree. Assuming that we have a common epoch secret among the group members, then we can derive the sender keys using the secret tree. And the secret tree is created like this. It's a lot of code, but it's like each user is assigned a leaf in the tree, and from the base encryption secret, we recursively populate the tree down with a left hash, right hash, left hash, right hash. Then we get the leaf keys. Then the actual ratcheting part looks like this in the actual code, but it essentially boils down to this. And you can see that it is really similar to the two-person method. We are going to derive the key and nonce out of the ratchet secret, and also a different secret out of the ratchet secret, which is the next generation's ratchet secret. So the first two parts were easy given the assumptions. But how do you actually get the commit secret consistently among each group member? This part is done by the hardest part of MLS, which is called tree KEM. In tree KEM, as in the secret tree, users are assigned a leaf node, and users have their leaf key pair, the public-private key pair. When a user wants to update their group secret, or their leaf key, what will happen is the user will create an update path. To do that, user generates a random path secret at their leaf. Then the parent path secret, let's say node 1's path secret, is created through hashing 0's path secret. 3's is created through hashing 1, then 7 with 3. Then you calculate up to the root, which is 7 in this diagram. And the commit secret of this tree is calculated from the root's path secret by taking yet another hash of the root's path secret. To convey that to the group members, when 0 creates its update path, the yellow, we find the copath nodes along the update path, which are green. And if all parent nodes in the tree, like 5, 9, 11, 13, if they're all populated, we encrypt the path secret to its to the key of its copath node. 1's path secret will be encrypted to 2, 3's will be encrypted to 5's secret, like that. And we can see this is possible in a 2-leaf tree, which is like a group with 2 users. User 1, which is a node in 0, creates an update path. So creates a secret at 0, takes a hash, and 1 has a path secret. Then the path secret of 1 is encrypted to 2's public key. And as node 2 knows the private key, so the 2 can decrypt the path secret on node 1, then get the commit secret out of 1's path secret. But what happens if there are blanks in the tree? What we do is we calculate the resolution of the copath node to figure out which node's keys are available. Then we encrypt the path secret of the update path node to each key. Let's see some examples. The resolution of the node indicated in the diagram, it will be a list of 3, 2 in that order. The indicated node has unmerged leaves, which will come up later. So its resolution is itself number 3. Then the index, the list of unmerged leaves, which is a list of 2. Then you can concatenate it, becomes 3 and 2. Then the resolution of the node, which is the root node, indicate that will be 3, 2, and 9, then 14. You take the left part's resolution first, and right part's resolution, which is a blank. So you go left first, and you go right. And so the resolution is used to figure out the set of keys that are necessary to encrypt to every node under that node. So what actually happens is you calculate the path secret for each node on the update path 1, 3, and 7. Then to encrypt one's path secret, you take the copath node 2. Then you take the resolution of the copath node and encrypt it to each key of the resolution. You do the same for 3, and you do the same for 7. So let's look at an example of how a group changes over time. A group is updated through messages called proposals and commits. And proposals are messages that add and remove users, notifies an update of user's leaf key, and it injects pre-shared keys. And also, commits will fix those proposals' informations and advances the group's epoch to a next generation. And update paths are conveyed in the commit message. If a user wants to join a group, then the users will publish their identity, which includes their public key, to a directory using a key package. And to create a group, user A creates an initial group with himself only. Then to add user B, A will download the key package of B, and then sends an add proposal, including the key package of B, then commits the changes. A sends a welcome message to introduce B into the group. To add C into a group of AB, the same happens for C. when adding, what happens in the tree is that you add the leaf node from the key package in the proposal to the leftmost empty node. To add to the top graph, what happens is node 10 is added. Then you will add the leaf index to intermediate nodes above that and to the merge list of those nodes. Then, to update a key, let's say user B wants to update. User B sends an update proposal notifying the group of its leaf key update. Then the other user, A, commits that update to include it in the next epoch. When updating, you replace the leaf node of the sender, let's say number 4, with the leaf node inside the update proposal. Then you blank all the nodes on its direct path up to the root, like in the blue. Then when removing a user, let's say Z wants to remove B, Z sends a remove proposal and a commit at the same time. In this case, B cannot decrypt the path secret included in the commit's update path, so B will not know the next epoch secret, so B's group cannot advance to the next generation. What happens is you blank the specified node in the proposal, let's say number 8. Then you blank all the nodes on its direct path up to the root, like an update. Then in this case, the right half of the tree is fully empty, so the tree is shrunk to the left half. So now, instead of 7, 3 becomes the new root. And if we are going to blank out nodes in the tree, when are the intermediate parent nodes going to be filled? They will be filled during the processing of a commit. And when processing a commit, the update path inside the commit will be merged into the ratchet tree. Then parent nodes are created based on the update path's node content. And we are omitting a lot of stuff because this is already getting too long for an any % speedrun. We are omitting stuff like injection of pre-shared keys, transcript hashes, which means the hashes that summarize the proposal commits that took place in the last generation, and signing and verification of messages. And there are 2 types of messages, public and private, which is one is clear text and one is encrypted. Let's show some implementation tricks that I did to do this in Ruby. And when you say binary protocols, you're going to say, oh, it's just a pack and unpack. It's very easy. But no, it doesn't work like that because MLS has variable length vectors and optional values in their structs. Variable length vectors look like this. So there's the length encoded in the first part, then the main body will be coming up after that. It is based on the variable length integer encoding in Quick, and you take a 2-bit prefix, and if it's 0, 0, the length will be the next 6 bits. If 0, 1, it's the next 14. Then if it's 1, 1, the next 30 bits will be the length. So you can encode a vector up to 2 to the 30th power bytes. Optional values look like this. There's a flag called present, and if the value is present, the present value is 1, then the value comes after that. You cannot decode this with an pack and unpack. So I define structs like this because there are lots of structs in MLS, so I wanted to have an easy way to define structs. So it is defined like this in the code. So a private message has a group ID, which is a vector, epoch, which is a 64-bit unsigned integer, and it has an 8-bit unsigned integer content type, authenticated data is a vector, and so on. So we have a class called MeloStruct base, which has the initialize and new and rest, which is the deserializer, and the raw method, which is a serializer. And these operate based on the struct constant that we defined in the class. And the deserialization happens like this. For like in uint 8, then we unpack the uint 16, unpack with a different format. Then when it's a vector, you're going to call vectors parse vec method. And we have a long list of types. And sometimes a class, let's say sender is nested in a framed content. So we have a class type which takes another argument. So we're going to recursively call new and rest on that class. And we can handle multiple instances of a class with that is encoded in a vector, like in this classes case. And we sometimes have values that depend on other values. Let's say leaf index only exists when the sender type is 0x01. So we're going to call the proc object that is defined this CTX sender type equals 0x01. If that's true, the predicate content will be true, so the element will be deserialized. Then, if not, we will get nothing. And if we're going to handle trees in Ruby, handling it with pointers, like the link-based trees, they are very hard because it's hard to do pointers in Ruby. So we're going to do it with an array because MLS operates on complete balanced trees, and they can be described with a flat array. For example, the tree on the right is a list of 0 to 9, then nil as the 10, and 12, 13, 14 will be nil too. And leaf nodes will be always evenly indexed. The parent nodes will be oddly indexed in this case. And we define operations such as left, which index is the left of this index, right of this index, which is a parent, which is a sibling, based on the array-based tree's characteristics. And these algorithms are conveniently defined in the appendix of the RFC. And also, this comes with this convenient serialization and deserialization format. And now, to finish this talk, let's talk about the ongoing and future work in introducing modern cryptography in Ruby. So we talked about hybrid public key encryption, and it is very nice because it makes it harder to misuse. And also, we have OpenSSL itself has APIs to do HBKE. And I talked about that at RubyConf Taiwan 2023, but haven't worked on it much since. But doing HBKE with OpenSSL's API a really good idea? I'm kind of iffy about that because the protocols need the whole cipher suite, not only the encapsulation, decapsulation, and open seal. And you also want access to the constants such as the hashes length, the key lengths that the cipher suite defines. And the OpenSSL's HBK context remembers those values, but you have to call it those functions separately. And some APIs of OpenSSL gem are intentionally undocumented, but I'm not going to fix it. You have to know what you're doing to use those undocumented APIs because it is dangerous. But I found like some missing or maybe not missing, but hard to do thing in OpenSSL. I found the difference of the Edwards curves, such as X25519 and the generic elliptic curves. They have different APIs, and so these have different APIs. So I had to come up with a convoluted workaround to get a consistent API, which is to check the correspondence of key pairs. And also to get EC public-private keys in a form that TLS and MLS wants. It is not apparent. For a private key, you call pkey.privatekey.2s in binary. But if you do that to a public key, it doesn't work. You have to convert it to a big number first, then you have to call 2s binary later. And also, it has a different API from X25519 and generic ECs. And there's additional features shipping in OpenSSL 3.5.0, which is post-quantum cryptography, which is algorithms that are strong against quantum computers, such as MLChem, MLDSA, and SLHDSA. And there is an internet draft that adds MLChem into MLS. And if we have MLChem API in Ruby, then we can implement this internet draft in Ruby too. And you might ask, MLS is end-to-end encryption, so it's a client-side thing, right? Ruby is a server-side lang. No, Ruby is not just Rails, because we have Ruby Wasm right now. So now that I've worked with OpenSSL and embed TLS in the Ruby ecosystem, I'm thinking of implementing a grand unifying cryptography API, or a unified API wrapper that calls OpenSSL web crypto API for the browser and embed TLS in embedded environments in a consistent way. So I wrote a very quick example of calling web crypto API's random number generator. And if we write wrappers for all other functions, all commonly used functions, and have a consistent API through web crypto and OpenSSL, then we can say that we can have MLS in the browser too. So to end this talk, let's answer the question in the description of this talk. Why do you need end-to-end encryption in Ruby? Or why do you need even modern cryptography in Ruby? Because 1, Ruby needs to stay relevant, or else people would just go to Python, Go, Rust, or whatever the cool kids use these days. But actually, Python doesn't have an MLS implementation yet, so it's a win for Ruby. And also, 2, Ruby needs freedom on the internet, and the free internet needs Ruby too. So that's the end of my talk. I'm going to give some quick shout-outs. First, shout-outs to the messaging layer security working group at the IETF, and shout-outs to protocol implementers in Ruby. The list is growing, and we have 2 more talks about network protocols today. You're definitely going to that one, right? And next, shout-outs to RubyKaigi 2025 organizer team, and especially local organizers who helped us make this conference a thing. And more shout-outs to the sponsors, especially the ones I have personal connections with, Kotak-san and Blumo Security-san. And I want to give one more special shout-out. And it's my grandmother. She used to live some blocks away from this venue. And please note the past tense. I wanted to invite her on stage today, but sadly, she passed away last October, just before Kaigi on Rails. This could have been the perfect opportunity to show what I've been working in the Ruby world and encryption and security. Still, I am very grateful and honored that we could have this RubyKaigi in my father's hometown, and I was able to speak in it. So if you have any questions or comments, please tweet at me at S01, or I'm also on Fediverse at S01 at Ruby Social, and also find me in drink ups or in the venue. I'm at Kotak's day 2 and day 4 drink up, and I'll be playing music in the Ruby Music Mix-In after day 3. So thank you.